In this video, we'll take a look at an example that will help you answer questions on written test number 3. There are a lot of applications of polynomials and of rational functions in real life. So we're going to take a look at an application of a polynomial. An open box is made from a square piece of cardboard 12 inches on a side by cutting identical squares from the corner of the box and turning up the sides. What is the dimension of the square x that results in the largest volume? So if you take a look at the picture, we've got a square and we're going to cut out little size x squares from each side. This will result in little flaps in the box. Think about these little flaps right here in blue. And if you turn these up, fold the corners up after the x's are gone, then what you'll end up with is a box that has dimensions x as the height, and then each side length is 12 minus 2x. So this little blue right here is the bottom of the box. The dimensions are 12 minus 2x on each side because you're cutting x from each side. So the volume of this box in terms of the x that we cut out, the side length, is equal to x times 12 minus 2x times 12 minus 2x, because volume of a box is length times width times height. So to explore a little bit, what is the volume of the box for different values of x? So if I take a look at Desmos, I've typed the equation into Desmos, and we'll take a look at the graph in a second, but I want to add a table, and let's take a look and see what happens for each side x. Okay, so we have x, and then volume of x. So when the side length of the box, if I cut 0, then the volume will be 0. So if you think about what that means, if I don't cut a square out at all, then I'm just going to have a flat piece of paper. If I cut out 1 inch and fold up the sides of the box, then my box has, let's see, if I 0, let's write it down mathematically, that would be 0 times 12 times 12, which is still 0. If I put in a 1, I get 1 times 12 minus 2 times 1 is 10 times 10, and the volume of my box is 100. If I put in 2, 12 minus 2 times 2, 12 minus 4 is 8, 2 times 8 times 8. So the volume of the box is changing for different values that I put in for x. So if we put in 2, we end up with 128. So notice the box volume is getting bigger. If I cut out a square of size 3, oh, now this box is getting smaller. 4, 5, 6, now I'm back to 0. How come? If I cut out a square of size 6, I'm basically cutting this piece of paper, the flat paper, into 4 pieces. So if I were to go any further, 7, 8, these are actually not possible. Okay, so let me get, so it would not be possible to cut out squares any larger. And the reason being, these should be negative. If I have a negative 12 minus 2, oh, I do end up back with a positive. But so I do get positive volume, but 7 and 8, I can't cut out squares that big. So the polynomial has domain negative infinity to infinity, but the domain reasonable for in the context of the box problem, I can only use x values between 0 and 6. If I cut out 0, I have 1 big piece of paper. If I cut out squares of size 6, I have 4 pieces of paper. So it has to be between 0 and 6. So let's graph the function on the domain and find the relative maximum. So what this function represents it represents all the different values of the sides, all the different volumes of the size x cut out of the box. I only want the domain between 0 and 6 So I'm going to adjust my viewing window. Use the wrench to do that. For the x-axis, I'm going to set it at 0 to 6. Step means what do you want to count by? I'm just going to count by 1. The y-axis, 0 is the smallest volume. And then I'm going to guess, I think I put in there 140. Use 140 and let's see if the graph shows up. Okay, it does. So I'll use step 10. So there's my graph. So this represents the possible volumes of the box as I cut out x from the side. So the volume of the box increases for sides until I get up to this very top piece. If you click on the graph in Desmos, the maximum value will show up, 128. And then as I cut out larger values of x, the volume of my box gets smaller until the volume is 0 down here at 6. So 128 is the maximum value. So graphing the function and finding the relative maximum using Desmos, you click on Desmos and that will give you the maximum. So the maximum was 128. So actually the maximum, relative maximum, is the y-coordinate 128, and it occurs at x equals 2. So what length x should be cut to maximize the volume? We should cut 2 inches of each side of the square out of the box. Cut 2-inch squares out of each corner. And the maximum volume is equal to 128 cubic inches. So if you also wanted to know what are the dimensions of your box, if you cut out squares of size 2 from each corner, then the height of your box is going to be 2. And the length and the width, since it's a square, this is going to be 12 minus 2 times 2, which is 8. And this is also going to be 8. So the dimensions of your box are 8 by 8 by 2 for a volume of 128 cubic inches and 2-inch squares out of each corner.